All right, let's dive into something pretty wild. We're going to explore a radical new geometry, a theory of morphogenesis that tries to describe, well, everything. We're talking from the shape of a plant all the way to the structure of a thought, using a completely new set of rules.
It all kicks off with this massive puzzle. We have these mathematical laws, right? They can predict the motion of galaxies with just breathtaking precision. But then, you turn that same powerful mathematical lens to the living world, and it kind of falls apart. Why is it that we can't write a simple, elegant formula for just one single, unique plant?
And look, this isn't some new problem. The great mathematician I.M. Gelfand, he perfectly described this gap. He called it an inconceivable ineffectiveness. I mean, think about it. Math is supposed to be the language of patterns. So why does it go completely silent when it's faced with the boundless creativity of life?
So, yeah, to bridge that gap, any new theory of form, or what scientists call morphogenesis, has to overcome some serious challenges, the kind of challenges traditional math just wasn't built for.
Okay, so what are we talking about here? Well, a true theory of form can't just describe some perfect, idealized flower. Now, it has to describe your flower, the one in your garden with all its unique little imperfections. It needs to account for its entire history, every twist of the stem, every single reaction to sunlight. And it has to work for everything, from a plant to a galaxy, from a bridge to an abstract idea. And here's the kicker, the ultimate goal. The model can't just be a good approximation. It has to be the object.
So, why does math struggle with all this? Well, the reason is buried deep in a foundational assumption, one we've been making for over 2,000 years. It's an idea so fundamental we barely even notice it's there. And that's the idea of the perfection of the circle. Think about it. From Newton's measure of curvature all the way to quantum mechanics, our science is literally built on the idea of a rigid, perfect, symmetrical circle. A place where distance is the same in every single direction. But nature isn't like that, is it? Nature is flexible, its symmetries are way more complex, and it's almost never the same in all directions. The physicist Richard Feynman, he just captured this beautifully. He pointed out that our minds are kind of hardwired to see the circle as perfect. So the moment something is just nearly a circle, we see it as flawed, as an error. And that mental block, it's kept us from seeing the inherent perfection in nature's own shapes. So, the big question is, how do we break free from this tyranny of the circle? Well, the first step was a massive breakthrough, and it's called the superformula. And this is the power of the superformula. We're talking about a single, elegant formula that just by tweaking a few parameters, things that control symmetry and curvature, can generate an absolutely incredible diversity of shapes. It can smoothly morph a circle into a square or a starfish, or just countless other forms we see in nature every day. And the best part? No more approximations.
Okay, so how does it work? Well, instead of a rigid ruler drawing a circle, imagine a flexible, totally elastic one. The superformula basically tells this ruler exactly how to stretch and contract as it rotates. So to our eyes, it looks like it's drawing a square. But here's the cool part. From the inside, within its own geometry, it thinks it's still drawing a perfect unit circle. The shape itself is defining its own space. It's a bit of a mind bender, right?
And let me be clear, this isn't just some neat mathematical trick. The superformula has been used to successfully model over 40,000 distinct biological shapes, and with incredible precision. We're talking bamboo leaves, tree rings, even bird eggs. The bottom line is, it actually works.
But the success of the superformula, it wasn't just about finding a clever equation. It was a huge hint that our very definition of space was just too rigid. And that led to a much deeper, much more radical idea. What if we had to redefine the most fundamental object in all of geometry?
And right here, this is the true conceptual leap. For literally thousands of years, a point was defined as having no size, no dimension. It was just a position. But this new geometry completely flips that on its head. It starts with a simple but incredibly powerful new definition. A point has size and shape. So, how on earth does that work? Okay, imagine a point that's made of some infinitely stretchable material. You can take that single point and stretch it out into a line. Then, you can stretch that line into a surface, and then stretch that surface into any object you can possibly imagine. Every single form becomes just a different extension of the exact same fundamental point. And from that one single core idea, you can build an entire formal geometry. And you can do it with a set of rules that is just stunningly minimal and elegant.
I mean, look at this. This entire framework is built on just 5 simple statements. That's it. The axioms? They basically say that every point is unique, but also, and this is key, that any point can be morphed into any other point. Then you have the postulates. They give it the power of infinite extension, so it can grow outwards, and infinite intension, so it can shrink inwards, carrying all its information right along with it.
Okay, so when you have a geometry built from these rules, what does it all mean? What's the big picture? Well, the implications go way beyond just describing shapes. They start to blur the very line between our scientific models and, the actual world they're supposed to describe.
Because think about it. If a point now contains all the information, its size, its shape, its history, and it can be continuously morphed into the object itself, well, then the mathematical model isn't just a good enough picture anymore. The model is the object. They become identical. They contain the exact same information. The distinction between them it dissolves.
Which really brings us to this profound thought from the Nobel laureate Barbara McClintock. She said, basically everything is one. And if you think about this theory, it makes you wonder, if every single form, every star, every cell, every thought is just a different transformation of a single, infinitely flexible point, what does that say about the nature of reality itself? Maybe the lines we draw between things, maybe they're just an illusion after all.